Okay, in this problem, we're asked for what is the electric potential at point C, which is some distance A above the midpoint of a long rod that has length L and uniform charge density lambda. So we want to find the electric potential at point C. So to find electric potential, we know that the total electric potential is going to be the integral over each little bit of potential. We add up all the little bits. And a little bit of potential is K times a little bit of charge dq divided by distance r. So let's ask, what do we mean by dq? What do we mean by r? dq is a little bit of charge along our rod. So let's indicate this part as our dq. dq we write in terms of the density and the length. So the density is lambda. The length is a little bit along the horizontal. So that length we would call dx. R is from our charge to our point. So this distance is r. We put our coordinate system, so our origin is right here. So there's the origin. So our distance x is from here to here. And our distance above is a, so r is equal to the square root of x squared plus a squared. So there's our dq, there's our r. Let's put those in the problem. So we've got the integral of k times lambda times dx over the square root of x squared plus a squared. We'll take our constants out front. So k is constant, lambda is constant. We've got the integral of dx over the square root of x squared plus a squared. We have to go over the limits of our rod. So the limits go from one end of the rod down here, x initial, to the other end of the rod, x final. Our x initial is at this end, so that's minus L over 2. Minus because it's to the left of origin, L over 2 because it's minus half the length of the rod. And our x final is to the right of the origin, it's positive, and it's the other half of the rod, so to plus L over 2. So we'll fill in our limits here. Next, we'll evaluate the integral. So the integral of 1 over the square root of x squared plus a squared is the natural log of x plus the square root of x squared plus a squared. Then we have to evaluate that at the limits, so L over 2 and minus L over 2. So we have to put in our L over 2's and subtract them. So we get k times lambda outside. The natural log of x, L over 2, plus square root of L squared over 4, because L over 2 squared would be L squared over 4, plus a squared. And then we subtract natural log of minus L over 2 plus square root minus L over 2 squared is still L squared over 4 plus a squared. Close the brackets. So there's our potential. We could live with leaving it like this, or we could simplify a little bit by dividing these two arguments. So that would be k times lambda times the natural log of L over 2 plus L squared over 4 plus a squared divided by minus L over 2 plus L squared over 4 plus a squared. And then if we wanted to make it a little bit simpler still, we don't have to because this is okay, but we could multiply top and bottom by 2 over L, and then that would give us, so if we wanted to, we could times by 2 over L here, times 2 over L here, and that would give us k times lambda times the natural log. L over 2 times 2 over L would give us 1, plus. Multiplied inside, that would give us 1 right here, plus, and then we multiply it right here, and that would give us 4 times a squared over L squared. And then on the bottom it would be the same, but we would have a minus 1 here. Okay, you wouldn't have to simplify it down this far, but it is just a little bit nicer because we don't have quite as many L's in there. So that's the electric field above the midpoint of a rod with charge density lambda and length L.